Well, hey, welcome to Quick Soil Mechanics Lessons with Brian. Today, liquefaction simply explained in 12 acts. Act 5, stress paths, and some cleanup. So let's go back to our axes, normal and shear stress. We've got the point at the origin. We're going to run some isotropic consolidation. That means sigma 1 equals sigma 3 and tau equals 0. So we bring that out along this x-axis to the final point that we call the initial confining pressure. We put our failure envelope onto here. We start loading this thing up in triaxial compression. Sigma 1 is increased, critical stress. Sigma 3 and sigma 2 are held constant. So what happens to that circle, of course, is that it grows and grows, except sigma 3 stays the same place. We're looking at total stress until it hits that failure envelope. Well, how does it get there? There's an infinite number of circles in between there. If we connect the top points of those circles together, forms a straight line with a one-to-one slope. And this is the MIT stress field connecting the tops of the circles. And we can add S and P to the axes. And S and P have these formulas, and those define the types of the circles. So this is the total stress path in the MIT stress field. Okay, and we've got a Cambridge stress field, which instead of S and T has P and Q. They have these formulas, and instead of a 1-to-1, it forms a 3-to-1 slope in total stress. And this is the Cambridge stress field, and this is the total stress path in the Cambridge stress field. Okay, so let's look at a point in a triaxial shear test. This is the total stress Mohr circle, just some point in the test, and this is the effective stress. And the difference between those two, I think everybody knows, is the core pressure. And because we have effective stresses, we need to put an effective stress action angle on here too. So let's consolidate our sample and put our circles on here. So we have total stress in black, effective stress in red. So we're building up that circle just like we were before. So sigma 1 is being increased, sigma 3 is remaining the same. The difference is the core pressure. So there's the effective stress version of the circle. So total stress is growing just like it was. The effective stress is going wherever it wants to, whatever the core pressure says. So it's not following any kind of logic like the total stress is. So we build that and build it until we hit the failure envelope in total stress and have a similar circle in effective stress. So just plotting those total stress points on there like we did before, straight line, one-to-one slope. But if put in effective stress, we hit the tops of the circles. It doesn't make any apparently logical path. So we have our two different stress paths, total and effective stress. That's kind of a mess that way. So we can simplify it and just put it this way. And we don't need those points because those are imaginary in-between points on a circle. So we've got the entire history of those circles, where they started and where they ended. And the total stress path is the effective stress path. So let's look at some typical stress paths, still in MIT space, where we're looking at the top of the circle. So this is an effective stress path for a normally consolidated clay. That's what a normally consolidated clay will always behave like. Now, if we've got a different situation, this is what a compacted clay looks like. This is what a lightly over-consolidated clay looks like. And if we put in here this one-to-one slope line for assessing this, we've got, in this case, heavily over-consolidated clay because it's crossed over that one-to-one line. So we know it's heavily over-consolidated. And that's the shape that these stress paths will always take when they're under these conditions. Now let's just extend that failure envelope up there and say, hey, why none of those hits the failure envelope? Well, you're right, because we're looking at the top of the circles and not the tangents. So we have this other line here called the KF line, or the failure line, and that sits at an inclination of theta. So in MIT space, tan theta equals sine phi prime. And that's just because it's a simple trigonometry problem here, where we've got two different right angles, and that's a simple transformation from theta to sine phi. Cambridge space is a little more complicated. So we've got this formula for sine phi prime. And now you might say, well, what if there's cohesion? In most cases, we don't have to worry about cohesion because it doesn't exist for most mining products, heap leach facilities, tailings, waste rock. It just doesn't exist. It exists in rocks, but if it exists in a soil, it's usually very, very minor. So we can usually disregard that and force the failure envelope through the origin. So that's quite a bit of information for today, and that cleans up some things that I left hanging there, and I think we have a little bit of understanding of why the stress paths don't hit the friction angle failure envelope on the KF line, and why I don't have anything that shows a cohesion. I think that's an easy thing for undergrads to be taught as a cohesion, but in most cases it just doesn't exist for soils. Wanted to leave you with a quote from a textbook that I refer to as Volume 3. In that text it says, in view of the ease with which stress paths can be plotted and failure envelopes derived, it seems remarkable that the cumbersome method of plotting Mohr circles has persisted for so long. For an undrained test in which pore pressure is measured, a stress path gives a much clearer indication of the behavior than the combination of conventional plots of stress and pore pressure change against strain, to which Mohr circles add little. And I fully agree with that. I would much rather see a stress path than a Mohr circle because it's more important to see how the circles got there than just the end point of it. And with that, I will leave this lesson and hope you enjoyed it, hope you learned something, and I will see you next time.